BC Chemistry, Unit 4, Infrared Spectroscopy. So in this session, we'll talk about how do we use the infrared section of the electromagnetic spectrum to analyze mostly functional groups. The study design requires us to know how infrared radiation interacts with the bonds of the molecule, and then how do we use that to identify the functional groups that exist in the molecule using the characteristic absorption bands. Okay. So IR, how does IR work? Well, normally covalent bonds can be thought of like springs with weights on the end of them. So they normally vibrate at their own frequency. They can also absorb energy and vibrate more. So the vibration of different bonds will be different. Have a look. If you have heavier atoms on both sides of the bonds, then the vibration will naturally be slower. Okay? If you have stronger bonds and relatively more lighter atoms, then the bond itself will vibrate slightly faster at a higher frequency, right? Okay. So different bonds will have different vibration, and they can absorb different amount of energy and vibrate even more. They can also undergo stretching and bending, really depending on what kind of energy they absorb. Right? Okay. So the amount of IR absorbed is different depending on the bond and the mass of the atom. So even if you have both of the double bond, but because the atoms attached to the bonds on both sides are different, so they will absorb slightly different amount of energy, and therefore being identified as two different structures, alkene or a carbonyl group. Right? So how does that look like? We have a simulation here. When they absorb energy, they literally become more charged and vibrate a lot more. And based on the amount of energy they absorb, we are then able to identify what kind of bonds are there in a molecule. Okay. So how do we read a IR spectrum? So notice that for IR, the spectrum, the absorption, looks a lot like some kind of liquid was tipped over and was falling down on a wall, right? So the absorption bands appear to be inverted. Okay? So the vertical axis is the transmittance. Transmittance is the opposite of absorption. So because in IR we actually measure how much they absorb. So when we talk about peak, it's actually a dip. So basically, this is the peak that we're talking about. This is how much energy was absorbed by a particular bond. Okay. The horizontal axis gives us the wave number. So you notice that towards the right-hand side, so it's a little bit counterintuitive because the larger wave numbers are on the left-hand side, and it actually decreases as we go along towards the other end of the x-axis. Okay? So the higher frequency is on the left-hand side, and the lower frequency is on the right-hand side. We use IR normally to qualitatively identify functional groups. Now, different types of covalent bonds absorb IR radiation with a characteristic range of frequencies. Okay? That allows us to identify the functional groups. So you can see that the single bonds with hydrogens are mostly on the higher end of the spectrum, and followed by the triple bond and then the double bond. And you notice that the carbon single bonds, okay, here the higher frequency normally has the hydrogen single bond. The carbon single bonds are at a lower frequency. You'll notice that the single bond, triple bond, and double bonds all occupy a different region. So normally we don't really need to trace a particular bond and which absorption, which peak it is. And in fact, various single bonds and double bonds in the same region have very slight different absorptions. Okay, it is rather harder to tell between the absorption of OH and an NH as versus telling the difference between a OH absorption versus a carbon-carbon absorption. Okay, so that's normally how we use IR. We're using that to identify, oh, this peak could be the single bond here, that peak could be a double bond, and then with the assistance of a empirical formula or a molecular formula, then we are able to sort of guess what kind of bonds result in what kind of absorption. So here, the lower region of the IR spectrum is what we call a fingerprint region. Those regions, the absorption patterns, are unique to each individual molecule. It's like the fingerprints of a human being. We'll have different fingerprints, and different molecules will have different fingerprint region in IR. Does this help us to identify what it is? Well, unless you have a huge amount of data with a facial recognition software to run through it. Otherwise, it's actually hard for us to use that region to tell what kind of bonds is responsible for what kind of peak, because they're all unique. There's no observable pattern. So normally we don't really use the fingerprint. What we want to focus on is the part at higher frequency, because then we will actually have fewer absorption bands, so we are able to identify when we see them. Our data book presents us with a list of absorption for different bonds, and it even distinguishes between the same carbonyl group, so carbon-oxygen double bond, in different environments. Well, first of all, I want to draw your attention to here. Although we are given the absorption bands for chloroalkanes and alcohol ester ethers, the carbon-oxygen single bond, because their absorption bands falls into the fingerprint region, so we barely actually use them because there are too many absorptions there. We can't really tell which one is it, or we can barely tell if it exists or not. Okay? So these two set of data, we don't normally use them. And then looking at all the different carbonyl groups, you'll notice that they all have different, slightly different absorption bands. Sometimes they even overlap with each other. Well, this is because the same bond is being surrounded in a different environment, different atomic atom environment. Therefore, they're slightly different. So in IR, normally the first couple of steps that leading us to identify the functional group, we don't really use these set of numbers. We only use the regions. So all of them falls in around 1600 to 1700 or even to 1800. We're using that particular region to tell us it could be a carbonyl group there. And then most often we need to use other information to help us determine if it's actually a carbonyl group that's an aldehyde or the carbonyl group that's actually an ester. Okay, so we don't really use these particular numbers until the very last few steps, helping us to confirm if it's an ester or if it's an acid. Okay, and then we have the carbon-hydrogen bond. You'd be like, what do you mean by carbon-hydrogen bond? Doesn't all compounds, all organic compounds have carbon-hydrogen bond? Yes, it is. It is the absorption that every compound would have. But because the carbon-hydrogen double bond is in a different environment when there is a different functional group around, their absorption might be different. Sometimes strong, sometimes wide absorption band.